IGCSE Computer Science, Syllabus Statement 1.3.1a, understand and define the functions of not, and, or, NAND, NOR, and XOR gates. So, this is the start of topic 1.3, which is the longest topic in the course, because it covers hardware and software. And yeah, it's just pretty long. So we start off with logic gates. So what are logic gates? Well, these are logic gates here. Well, 6 of them. And they're basically related to binary. So logic gates are used in electronic circuits in computers. So your computer in front of you, or like phone or iPad or whatever you have, it's made up of thousands of these logic gates, and we're about to find out what they are now. So they basically take in binary input and well, output binary as well. So input binary, output binary, and you'll see how this works. So we'll start with the NOT gate. So the NOT gate looks something like this. You're going to have to know these symbols for the exams if you're constructing logic circuits. However, on the 2015 winter papers, I noticed that there were no logic questions, which was a bit sad, because this is quite an easy topic once you get the hang of it. But yeah, just in case your exam actually does happen to have logic in it, then you might as well be prepared. So yeah, when we see a logic gate, we have an input and an output, so A and X respectively. And what we can do is we can give A a binary number, and X will give a binary number, or it'll output a binary number. So, say for example, we gave this 0, then 1 would come out in the NOT gate. And we can actually, and vice versa, but we can actually represent this using something called a truth table. So input 0, output is 1, input's 1, output is 0. So a NOT gate is basically the opposite. So basically what this is here, this small thin line, is basically a wire. So in a physical circuit, like NOT gates, and remember that binary we can say is kind of like electricity, so off and on is 0 and 1. So it's kind of that idea. So when you pass electricity into a NOT gate, then no electricity comes out. And that's sort of what the NOT gate represents. There's also logic notation for this gate, for every gate actually, but this is the one for this gate, so it's not A. And then there's Boolean algebra, which is this. So you're going to have to know this for the exam as well, both of these. And we'll get back to using these when we look at logic circuits, as these will become a little more complex. And this course doesn't ask you to simplify it, but it's still good if you can, like, you know. But I mean, I don't know. They might ask you to give the full Boolean algebra expression, but you know, it's still cool if you simplify. So let's look at the AND gate. So the AND gate looks like this, and you'll notice that it takes 2 inputs instead of 1, like the NOT gate. Well, this behaves a bit differently. So we get inputs A and B and output X. So the truth table would look something like this. So if we give A0 and B0, the output would be 0. A0 and B1, the output would be 0. A1 and B0, the output would be 0. But A1 and B1, the output is 1. So you can kind of see why it's called the AND gate. So this and this have to be 1 in order for this to be 1. So the logic notation would be X equals A and B. Boolean algebra would be X equals A dot B. And you'll also see when we look at logic circuits that we can use, as said, logic circuits, basically a bunch of logic gates, and you'll see how that works. And I'll also show you that, like, logic circuits can be used to perform functions, such as adders and subtractors can be built with logic gates. And I'll show you a bit of that later on in another video. So we had 2 inputs for the AND gate, but we can actually have more. We can actually have 3, 4, 5, or however many we like. So this is how the truth table would look if we did this. So we'd have the inputs A, B, and C, and the output X. So A and B and C give 0. Rather, 0 and 0 and 0 would give 0. 0, 0, 1 would give 0, and so on, actually, until we get to this, where it's 1. So you can see that all of these have to be 1 in order for this to be 1, because it's A and B and C. The OR gate is a similar idea, but of course a different truth table. So again, we get the inputs and the output, but for OR, 0 or 0 makes 0, 0 or 1 makes 1, 1 or 0 makes 0, and 1 or 1 makes 1. So why is this the case? Why is 1 or 1, why does 1 or 1 make 1? Well, basically, the OR gate isn't exclusive, and which is what the XOR gate is for. It's exclusive OR. So the OR gate isn't exclusive. It can include multiple 1s for its input in order for the output to be 1. But as long as, basically for the OR gate, as long as any input has 1, or any, like, 1 or more inputs have 1, then the output is 1. So the logic notation would be this. Boolean algebra would be x equals a plus b. So 3-input OR would look something like this. So remember that like any input, 1 or more inputs can be 1 in order for x to be 1. So it looks like that. So the XOR gate, as you may have guessed, would look something like this. This is the, of course, the gate itself, and the truth table looks like this. So as you notice, the XOR gate will not produce 1 if both these inputs are 1. So it'll only accept one or the other, basically. So it's exclusive. And the logic notation for this would be this. Would be A XOR B. Boolean algebra would be A plus circled B. Now, I don't know if this will be acceptable if you write this in the exam, but you know, try it out, because this is actually the official symbol for XOR. So yeah. So what would a 3-input XOR truth table look like? Well, you might find it a bit weird at first, but it actually does kind of make sense. So let's take a look. That looks fine, that looks fine, that looks fine. Okay. So here we get 0, 1, 1, 0, which can be expected. If you cover up the A, B XOR C would make 0, but there's a 0 here, so doesn't that... Well, no, not really. Because the XOR gate actually kind of works like this. So only one input, and only one input, can be 1 in order for the output to be 1. So if it's 0 or 2 or more, then the output is 0. So that's how a multi-input XOR, well, an XOR gate itself works. So now we have a few more gates left. We have NAND and NOR. So what are they? Well, we got the N from NOT and the AND from AND. So that would make NAND, wouldn't it? So NOT and NAND. Well, that's it. So it's basically you put a NOT gate in front of an AND gate. Well, when I say in front of, I mean like the output of the AND gate will be the input of the NOT gate, and you can make a NAND gate. Now, NAND gates are quite special, and we're going to see how they are special later, but they are special, and we'll get to that. So let's take a look at the truth table for a NAND gate. I was about to say trace table, which is what we'll cover in practical problem solving and program. I don't know why that title is so long. Why can't it just be problem solving? Like, it's not really programming. It's like, I mean, it kind of is programming, but like pseudo programming. It's alright. So here we have a 1, here we have a 1, here we have a 1, and here we have a 0. Now what do you notice about the outputs here from this truth table? Well, if you go back back to where we looked at the AND gate in this video, you'll notice that the outputs are the exact opposite. So the AND gate's truth table would be 0, 0, 0, 1, but the NAND gate's truth table would be 1, 1, 1, 0. And the logic notation was obviously this. Boolean algebra would be this. So this, just the A dot B would be an AND, so we just stick a dash on the top of it to make it NAND. So it's not AND. It works like that. So a 3-input NAND would look something like this. So go back to the 3-input AND, and it's basically the exact opposite. So the NOR gate is the same principle. We stick a NOR gate in front of the OR gate. Oh, sorry, stick a NOT gate in front of the OR gate to make a NOR gate. So NOT OR. So let's take a look at the truth table for this. So 0, 0, 1 as expected, 0, 1, 0, 1, 0, 0, 1, 1, 0. So this was expected because it's the opposite of the OR gate truth table. And same thing with the like a bar up here. It's knotted. So the entire statement here is knotted. So a 3-input NOR would look something like this. Ooh. So now this isn't actually listed in the syllabus, but it's still good to know it because, like, why not? I mean, why are they getting us to do XOR without having to put a NOT in front of it? So we get XNOR, not NEXOR, XNOR. So like exclusive NOR. So that's basically what it looks like. It's not, again, it's not in the syllabus, so I wouldn't bother trying to impress the examiner by using this. But if you want to, go ahead and try it. It's like, yeah, well, yeah, whatever. Alright, so the truth table for this would, of course, be the NOT of the XOR. So it would be 1, 0, 0, 1, and of course the logic notation would be that, Boolean algebra would be that. So let's take a look at a 3-input XNOR gate before we wrap up this video. Just so you get the idea, it's the opposite of the 3-input XOR gate.